For years, physicists built the perfect quantum safe box, a Majorana qubit so protected that information inside could not be destroyed. The problem? It could not be read either. Billions in research were frozen at a wall the field called impossible. Then a team from Delft and Madrid cracked it and published the proof in Nature. To understand why that is seismic, you need to know what made this qubit untouchable. On February 16, 2026, Nature published a headline that sent shockwaves through physics. Researchers from TU Delft and the Madrid Institute of Materials Science had achieved the first real-time readout of a Majorana qubit. The paper, DOI 10.1038S415860250999277, documents what leading theorist Ramon Aguado calls a pioneering feat, one that turns the field's defining paradox on its head. For years, Majorana qubits were engineered to be the ultimate safe boxes for quantum information, locking data inside a fortress of non-local encoding so robust that even the environment could not break in. But that same protection made them unreadable by any conventional means. Billions of dollars and decades of research hit this wall. If you cannot read the qubit, you cannot use it. The Delft ICMM team result is not a simulation, not a theoretical model, but experimental proof. Their collaboration, forged under the QKit project, brought together the hardware expertise of TU Delft and the theoretical firepower of ICMM Saskii. Together, they built a minimal Kitaev chain, a modular nanostructure that does not just host Majorana zero modes, but lets researchers control them from the ground up. Using a quantum capacitance probe, they access the hidden state of the system globally, distinguishing the qubit's even or odd parity in real time. Aguado's own words echo across press releases. Safe boxes for quantum information, now finally openable on command. The stakes are enormous. This is the moment the industry has waited for, the day the impossible problem became a solved fact in a peer-reviewed journal. For every company betting on topological quantum computing, the question is no longer if this future arrives, but how fast. To grasp why, it is critical to understand what makes Majorana qubits so radically different from anything that came before. Majorana qubits were never supposed to be readable. Their entire advantage, what set them apart from every fragile, error-prone qubit before, was this. Information is hidden, not in one spot, but smeared across the ends of a quantum wire, encoded in the shared state of paired Majorana zero modes. That is the essence of topological protection. Local noise can batter one end, but unless the whole system is disturbed, the qubit's parity stays locked. The result is a fortress, a safe box for quantum information, as Ramon Aguado put it. But here's the catch. If the information is not anywhere local, how do you ever open the box without destroying what is inside? For years, this was the paradox that haunted the field. Every attempt to measure the qubit with a local probe, whether charge sensors, tunneling contacts, or spin detectors, hit a blank wall. The measurement apparatus would poke at one end, but the encoded information by design was nowhere to be found. Experimentalists could confirm the presence of zero bias peaks or see hints of Majorana physics, but the actual parity, the bit that matters, remained invisible. Skeptics, even those sympathetic to the theory, started to doubt if any measurement could ever access the state without breaking the very protection that made Majorana qubits valuable in the first place. One independent experimentalist, long unconvinced by the parade of indirect signatures, summed up the frustration. If you can't read the qubit, it's not a qubit. The search began for a different kind of measurement, a probe that did not just look at one end or the other, but could interrogate the entire system at once. The challenge was clear. Find a way to read the state in a global way, without collapsing the protection that makes topological qubits worth pursuing. Until that barrier fell, the promise of a scalable, fault-tolerant quantum computer would remain out of reach. Inside the Delft lab, the heart of the experiment looks almost austere. just two quantum dots bridged by a superconductor, the minimal hardware needed to build a Kitaev chain from the ground up. This is not a sprawling quantum processor with thousands of wires and control lines. It is a precision instrument, engineered to expose the secret at the core of topological quantum computing. The breakthrough lies not in brute force, but in subtlety. Instead of probing the ends of the chain, the researchers couple the entire device to a radio frequency resonator, a circuit element sensitive to the system's quantum capacitance. Quantum capacitance is a measure of how easily the device's charge state responds to tiny changes in voltage. But in this setup, it does something far more profound. It acts as a global sensor, attuned to the total quantum state of the system, not just the local properties of a single site. When the parity of the Majorana qubit flips, from even to odd or back again, the quantum capacitance shifts. The resonator, in turn, picks up that shift as a change in its frequency response, translating the hidden non-local information into a real-time electrical signal. For the first time, the elusive parity, the very bit that defines a Majorana qubit, can be read out directly without disturbing the topological protection that gives these systems their edge. The entire chain is probed as one, sidestepping the blindness of local measurements. This is not a simulation, not a hint or an indirect effect, but a direct experimental window into the safe box itself. The industry's unsolvable measurement problem has been cracked, not by brute force, but by a sensor that listens to the whole system at once. Numbers in this field are not just data points, they are the measure of what is possible. When the Delft ICMM team published their traces, independent experimentalists pored over the raw parity records. What they found was not a fleeting signal or a statistical fluctuation. The parity state of the Majorana qubit held steady for over a millisecond, more than 1,000 microseconds of coherence captured in real time. These are not idealized, filtered results. The random parity jumps are visible, each one logged as a discrete event, with the system state flipping between even and odd. The pattern is unmistakable. The qubit's information, encoded non-locally, resists noise in a way no conventional device has achieved. To put this in context, the best superconducting transmon qubits, workhorses of today's quantum labs, struggle to maintain coherence beyond 100 to 200 microseconds. Here, the Majorana device surpasses that by a factor of 5 to 10, and does so without the layers of software, error correction that eat up 99% of resources in standard machines. For an industry built on the hope of scaling quantum processors, that difference is seismic. The checklist of requirements for practical quantum computing, long coherence, fast readout, error resilience, has always had a glaring blank under protected qubit readout. That box is now checked. One veteran experimentalist, known for skepticism after years of false dawns, said that if you see parity coherence above a millisecond in a system this minimal, you are looking at something fundamentally different. The numbers do not just suggest progress, they redraw the boundaries of what is possible. The field's most persistent barrier, reading out a protected qubit without destroying its state, has been crossed. For every company betting on topological hardware, the race is now about scale, not proof. Inside corporate labs, the news from Delft and Madrid triggered a scramble. Microsoft, already deep into topological hardware with its Majorana 1 chip, called emergency meetings to accelerate integration experiments. Teams at Google and IBM, long focused on transmons and surface codes, began reallocating budgets, shifting resources toward topological prototypes and cross-platform hybrids. Industry roadmaps, once built on 5-year cycles, were suddenly redrawn. Executives demanded new milestones. Replication of the Delft ICMM readout by 2027, integration into scalable processors by 2028. For the first time, Gantt charts replaced theoretical papers as the metric of urgency. One research and development director put it bluntly, if parity coherence above a millisecond holds in our systems, the scaling wall is gone. Every quarter counts now. Billions once locked in speculative research are being funneled into direct engineering. The countdown to practical, fault-tolerant quantum computing has begun, not in decades, but in years. The convergence of quantum and AI breakthroughs is no longer a distant scenario. Policy experts warn that by 2028 or 2029, the window for meaningful safeguards may close as quantum hardware and advanced AI begin to overlap in real-world systems. The implications ripple through every field. Quantum-powered models could accelerate drug discovery, break classical cryptography, and unlock climate simulations beyond today's reach. Concrete action is now urgent. Governments must update security standards, mandate quantum-safe cryptography, and require critical infrastructure to begin migration immediately. Regulators should enforce transparency in quantum and AI deployments, while workforce planners must fund specialized training to build expertise before the talent gap widens. The checklist is not theoretical. These are steps that determine whether society stays ahead of the next wave or gets swept under it. A qubit, once called unreadable, engineered as a safe box for quantum information, is now unlocked, experimentally, not in theory. The industry's billion-dollar blockade has fallen. Today, the only question left is speed. How soon will this shift remake what we call possible? The countdown has already started.